In the lower three panels, we'll replicate the exact same reasoning as the one we developed in the upper three panels, except we'll change one thing. Instead of assuming that the production technology has constant returns to scale, we'll assume now that the production frontier has initially increasing returns to scale that eventually becomes decreasing returns to scale. We'll begin with the blue and the magenta isoquants, and the only thing we're changing is the labeling on the magenta isoquant. It was 100 in the upper panel, it's now 80, which means that by doubling the inputs from point B to point A, we're now more than doubling output. In other words, we're on the portion of the production frontier that has increasing returns to scale. We then replicate the green isoquant from panel A, except that we change the label from 300 to 250. Now notice that when we went from input bundle B to A, we increased output by 120. When we then add the same increment of inputs in going from A to C, we're only adding 50 in output. Thus, we've entered the decreasing returns to scale portion of the production frontier. In panel E, we then again derive the short-run total expenditure curve for a fixed level of capital of 100 and the long-run cost curve. The long-run cost curve now has the shape that tells us that initially it's getting cheaper and cheaper to produce additional units of output, but eventually it gets more and more expensive to produce additional units of output. This arises from the initial increasing returns to scale that eventually become decreasing returns to scale. The short-run total expenditure curve for a fixed level of capital of 100 lies above the long-run average cost curve for the same reasons as it did in panel B, and it's tangent at point A prime for the same reasons as in panel B. And we'll again get U-shaped short-run average expenditure curves corresponding to different levels of fixed short-run capital. When capital is fixed to 100 units, then the average expenditure curve corresponding to that level of capital will contain one point that's derived from the production plan A. When capital is fixed to 50, the average expenditure curve corresponding to that fixed level of capital will contain one point that's derived from production plan B, and when capital is fixed to 150, the average expenditure curve corresponding to that level of capital will contain one point that's derived from the production plan C. The long-run average cost curve will also contain points that are derived from the cost-minimizing input bundles A, B, and C in panel D, and it will therefore contain the corresponding points from the average expenditure curves that also were derived from those input bundles. The long-run average cost curve is then the lower envelope of the short-run average expenditure curves that correspond to different levels of capital. We've drawn 3 of those here, but there are many more, and each one of them is tangent to the long-run average cost curve at exactly one point, at the output level, at which the capital that is fixed in the short run is exactly the right level of capital, or the cost-minimizing level of capital, to produce that level of output in the long run. We began in the top 3 panels with a constant returns to scale production technology because it's probably easiest to see the relationship between short-run average expenditure curves and long-run average cost curves in that context. But the reasoning is exactly the same in the lower 3 panels, and the end result is exactly the same. In both panel C and panel F, the average long-run cost curve is the lower envelope of the short-run average expenditure curves that correspond to different levels of fixed capital. The only real difference is that in panel F, the long-run average cost curve is U-shaped because of the initially increasing returns to scale that turn to decreasing returns to scale along the production frontier. In panel C, on the other hand, it's a horizontal line because of the underlying assumption of constant returns to scale.